Okay. Thanks, Sergio. So this is still in the inclusion exclusion chapter, but it's section 6.3. And this is on a topic called derangements. Talk about things being deranged. It's kind of an interesting terminology. But there's a famous problem that is associated with this. This is called the hat check problem. So it's often introduced in this context. So at a party, there are n people, each with a hat. So there are n people, and both of them have a hat, or all of them have a hat. So the question then, the little math problem with this is how many ways, it's combinatorics, so how many ways can the hats be distributed how many ways can the hats be distributed so that nobody gets their own hat back? This is, in words, this is the hat check problem. So you have, everybody has a hat. In how many ways can you pass those hats back out so that nobody gets the correct hat back? And such a distribution is called a derangement. So just by terminology, such a distribution is a derangement. So that's a new terminology here, a derangement. And the number of such derangements, is denoted as D sub n. So D sub n is going to denote the number of derangements. Okay, so we are going to try to get a handle on how many derangements there are of n objects. So a little more room here. Give everybody a chance to catch up. That's a lot of writing there. Steal this little here. Okay, so what we can do, guys, is as you might expect, we're just going to take the total number of ways of distributing these hats, which would be how many, by the way? N hats being passed to n people.
N factorial.
N factorial, right? So, you know, first hat, you got n people to choose from. Second hat has to go to somebody else. So that's n minus 1, and so on and so on. So there's n factorial total ways to distribute the hats back, and we are going to subtract violations. We're going to subtract the violations. What would be a violation? Well, if I got my own hat back, that's a violation, right? If Tanner got his own hat back, that's a violation. And we have lots of different kinds of violations for all n people, and some of those violations are going to overlap. So this is where the inclusion exclusion is going to come into it. So basically, the idea here is the strategy for D sub n. If I want to count what D sub n is we take the total number of ways to distribute the hats. This is n factorial. Total number of ways to distribute hats is n factorial with no constraints whatsoever. And we subtract we will subtract violations. Common strategy that we've certainly used quite a lot. So to set up the violations, I'm going to make some sets because I like to use the inclusion-exclusion principle in the context of sets. So I'm going to let A sub I be the set of distributions where the ith person gets their own hat. A sub I is going to be those ways of passing back the hats such that the ith person gets their own hat. Now, other people might get their own hat also. I don't care about that. I only care about the ith person. This would be with I ranging from 1 to n, inclusive. So A1 would just be distributions where the first person, that might be me, and these would just be distributions where I get my own hat back. That doesn't mean nobody else gets their own hat back, right? Several of us could, but this is the idea. And so what we know then is, I think we can all agree that the number of derangements would simply be n factorial minus those violations, and a violation is a distribution where anyone gets their own hat back. In other words, it's the union of all of these sets. Yeah. It's going to be the union of all of those, yeah. That's going to be it. Okay. Well, we know how to size up a union. Last week we talked about the inclusion-exclusion principle. And so let's just recall from last week when we were talking about this, that we have a nice, well, it's not a nice formula, but we have a confident formula for how to calculate the size of this union. A1 union A2 and so on up to AN. We can write that as, if you remember from last week, we start by adding up the sizes of all of the singletons. I'm going to skip putting indices on my summations. It's the same thing we've had before. But the point is it's alternating sums of various intersections. So the second set of terms that we would be adding up would be the two-way intersections, and we subtract that one, subtract the summation of all those. Then we add the summations of all of the three-way intersections, AI, AJ, and AK. It's back and forth and back and forth, plus, minus, and dot, right? And the last term, the very last one, if you remember from our inclusion-exclusion formula, there is a sign factor of -1 to the n plus 1 that has to get multiplied by the sizes of the intersections of all of the n sets. So that's what you would have. And what I really want to try to figure out with you guys now is what are the sizes of these sets. So let's just note that the size of A sub I is something we should be able to write down. So A1, I'm the first person. So if we're talking about A1, that would be a distribution where I did get my own hat back. As for the rest of you, I have no idea. There's n minus 1 of you, and you have n minus 1 hats, and they can be flung out there randomly, right? So would you agree that if I'm getting my own hat back and the rest of the hats are pretty much randomly permuted, that this is going to be n minus 1 factorial? Mm-hmm. Right? Because there's still n minus 1 hats that can go to any of the other n minus 1 people. That's the idea. So the idea here, maybe just to explain it, the ith person must get their own hat. All others are randomly permuted. So So everybody else's hat could go anywhere, any which way. Okay. By the way, this is sort of a little justification that's kind of nice, right? If you're writing up a solution to something, give me an explanation of where that's coming from. That's really helpful. And then maybe you don't have to do that for all of the subsequent observations that you're going to make if they're similar. What about a sub I intersect a sub j? This would be I'm getting my correct hat back and Tanner is getting his correct hat back. What do you think the number is going to be here? One more time? N minus 2 factorial. Exactly. Two of the hats are kind of automatically going back to their correct owners. All of the rest of them are being permuted any which way, right? So I'll just say similar justification here. That's totally okay. Basically, the I and j person have to get their correct hat back. Other than that, the rest of them are randomly permuted. Okay, and then let's just keep going. Well, actually, let me write down one more. So if I had AI intersect AJ intersect AK, in this case, 3 of the people have to get their own hat back, and the remaining n minus 3 are randomly permuted. So again, that's a similar explanation. And with that, I think I'm now ready to kind of work on this calculation. We're going to come up with a really cool number here, by the way. This is a really neat thing. I hope I'll be excited as it's something is going to show up in this combinatorics class that you would never think in a million years would be something that would be in this class. This class is supposed to be about nice whole numbers. 1, 2, 3, 4, 5, right? So let's just see what comes out of this. It's not going to be such a nice thing. I have to keep you on the edge of your seats a little bit. It is pretty interesting. Okay, so let's see if we can work out what this is actually going to get us. So what about the size of this union now? Because this is the part that we are going to subtract from n factorial. Okay, so we've got our formula here. The first thing we do is we add up the sizes of the singletons. Each singleton has n minus 1 factorial as the size of that set. And how many of those sets are there? N of them, right? So I'm actually going to write that out. N factors of n minus 1 factorial. That's this. Okay. Then I have a minus. Now the next terms are all being subtracted. The sizes of all of those subtracted terms is n minus 2 factorial. And my question for you is, how many of those are there? How many IJ combinations do you have here that are being subtracted? And choose two, right? We talked about that, I think, before when we were looking at the formula last week. There's n choose 2 factors. Each of them is n minus 2 factorial. Okay. The next one goes back to plus. And on this one, we would have n choose 3 and n minus 3 factorial, right? And so on and so on. So dot, dot, dot. And then, of course, we get to the very last one, and we still have, plus -1 to the n plus 1. We only have one term here. There's no summation. But I'm going to, just to be making it look like the other terms, I'm going to put an n choose n there. Okay. And then in terms of this factorial business, well, basically it's going to be n minus n factorial at that point. And some of those values are obviously degenerating, but I just like to make everything look the same. Okay. So I'm just going to clean this up a little bit. Okay, is everybody getting suspense, getting the suspense for this? The first term here obviously is n factorial. Now on this n choose 2, let me just remind everybody, n choose 2 is really n times n minus 1 all over 2. So this is an n and an n minus 1 together with an n minus 2 factorial, and then it's all over 2. So this is actually just half of n factorial. Actually, let's write it as n factorial over 2 factorial. Okay, what about the next one? Well, n choose 3, as you know, that is n times n minus 1 times n minus 2, all divided by 3 times 2 times 1, right? Definitely need you to know that. And the point being that the numerator of this tacked on with the n minus 3 factorial makes another n factorial here, and now on the bottom we have a 3 factorial. Okay, and so actually every single term seems to have this n factorial on top. If you look at it. And so we just keep going like that, and then when we get to the very end up here, well, we have minus 1 to the n plus 1. And I'm gonna think of this as n factorial, but divided by n factorial. You see, so whatever, basically whatever number was on the bottom of the binomial coefficient, that's how many factorials you have of it on the bottom. So just following the pattern, that's what you would have. Okay, does anybody see what kind of a strange thing is gonna show up here? Let's go a little further. Come over here and erase. That's the. It's so cool.
That's the meter.
It's a really interesting answer.
I think it's.
So now I'm ready to give you basically the theorem here, guys, and this is theorem 6.3.1. Okay, and what this theorem is basically just, it's a formula for d sub n. I will want you to know this for the exam next week, so if you need to put this on a flashcard or whatever, don't hesitate to do so. But we're taking n factorial and we're subtracting all of that, right? So we're subtracting, I'll put it in big brackets here, n factorial minus n factorial over 2 factorial plus n factorial over 3 factorial minus dot, 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 dot. And then we finally get to negative 1 to the n plus 1 times n factorial over n factorial. And I am going to take that and simplify it even a little bit better by factoring out an n factorial from everywhere. So I have an n factorial that I'm going to pull out of the entire thing. And what I have here would just be 1 left over. And then minus this. So if I factor out the n factorial, that just becomes a 1 as well. Would you mind if I write it as 1 over 1 factorial? You'll see why in a second. Okay, and then I'm going to factor out this n factorial as well. And notice there's, yeah, so this becomes a, oh, wait a second. No, I'm fine. I'm just alternating the signs. This is a double negative, right? So this becomes plus 1 over 2 factorial. And then the next one has a minus 1 over 3 factorial. And we alternate like that all the way down the line. On this last one, we had a negative 1 to the n plus 1, but I'm going to be distributing this minus to the very last term as well, which actually means it becomes negative 1 to the n plus 2, which I'm just going to write as negative 1 to the n. Okay, and then there is still an n factorial on the bottom of that as well. So you can kind of check me on that, right? If n is odd, then this term should be subtracted. If n is even, it would be added. But that's essentially what you would have. So this is a nice formula for d sub n, like so. Just to play with it for a second, I'm just to get some idea here. What is D1? How many ways, if there was one person at the party with one hat, how many derangements would you be able to do with that person's hat?
Would it be
Trick question.
Would it be 0?
Yeah, it's impossible, right? You have to give that person their own hat back. Does that work? If I plug in n equals 1, then in the brackets here, don't I end up with a minus 1 term on the end? So you started with 1 and then you just subtracted 1 and got 0. Yeah. What about 2? What should be the number of derangements of 2 hats?
1.
There's only one way. If me and Tanner each have a hat, we're either gonna both get the correct hat back or we'll both get the wrong hat back. Either way, there's only one of those that would be a derangement. You can check it into the formula here. 2 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial, and just make sure, does that really equal 1? The answer is it does. Okay. Let's do one more, just brute force calculation on this. How many derangements would there be of 3 hats? So I want to put the 3 numbers, 1, 2, and 3, into these 3 slots, but I don't want to put a 1 in the first slot, I don't want to put a 2 in the second slot, and I don't want to put a 3 in the third slot. Question would be, how many ways could you do that? If you don't want to hurt your brain too badly on it, you can also use the formula. 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, and all of that being multiplied in front by 3 factorial. So this is actually 1/2 minus 1/6, which is 2/6. In other words, 1/3 times 6, which equals 2. There's only 2 ways to do it. What are the 2 ways? Well, I can give the first person the second person's hat. I can give the second person the third person's hat, and I can give the third person the first person's hat. Now nobody has the correct hat. No number is in its correct position, in other words, right? Or I could give the first person the third person's hat. I could give the second person the first person's hat, and I could give the third person the second person's hat. These are the 2 derangements of 1 through n. So you can write out the derangement as a numbered list from 1 to n in some order, as long as the ith number is not occurring in the ith position. So you're imagining here that you've lined up the n people. So this is person number 1, this is person number 2, this is person number 3. And now you're telling me numerically which hat number do they get back. So the first person should not have a 1, the second person should not have a 2, and the third person should not have a 3. So far make sense? Okay, I'm gonna give you 1 minute, maybe 2.
Okay.
See if you can write out and find, without using the formula. Without using the equation, unless you want to just check your answer. See if you can write out the derangements of 4 objects. I'll just be curious how many we come up with. Has anybody found more than 9? Yeah, I think there's 9, and I actually think I've written them all down here. Notice that I didn't do them in order, I did really bad, but,
Same.
I got, 3 of them start with 2, 3 of them start with 3, and 3 of them start with 4. There's a little bit of a symmetry to them. But yeah, this is, kind of an enumeration exercise, but it should be 9, and of course you can check that using the formula as well, now that we have that as well. But yeah, it turns out, I think, to be 9. Okay, so just play with this idea a little bit. But wait a minute, Dr. Annan, I thought you were saying there was gonna be something other than whole numbers like 1, 2, 3, 4, 5 that was gonna be really cool coming into this whole thing. So far, it just looks like a bunch of, straight numbers here, whole integers or whatever. But there is something kind of cool, that I have to share with you here. I'll call this coolness. It's pretty neat. I would like to know, what is the likelihood? Can I ask a probability question? What is the probability that if you pass back the hats randomly, that it's actually a derangement? So I would like to phrase that or consider that. So the likelihood or the probability of a derangement. As soon as it's a probability, it's not going to be a whole number anymore, right? It's gonna be a fraction between 0 and 1. So I'll just call this the probability of a derangement, d sub n. And I think you all know how this works. You take, how many derangements you have, and you divide by the total number of permutations, which if we didn't have any constraints, it would just be n factorial. So you calculate dn over n factorial. Now, if you look at the formula for d sub n that we have in our theorem over here, if I want to divide that by n factorial, it's easy enough. I just get left over with the part that's in the brackets, which is 1 minus 1 over 1 factorial plus 1 over 2 factorial and minus ... The last term is -1 to the n divided by n factorial. So that's fine. We could think of that as the probability, but now I want to ask you, what happens to this probability as the size of the party goes to infinity? So as n gets really, really large, so as your number of hats goes to infinity, if I had 1,000 people with 1,000 hats, and I wanted to know what's the probability of a derangement, then we're basically taking some kind of a limit of this expression. The probability of a derangement would be the limit. Can I do limits in combinatorics? Limit as n goes to infinity of 1 minus 1 over 1 factorial plus 1 over 2 factorial minus ... And finally plus -1 to the n over n factorial, like so. And I'm wondering if anybody knows what that limit is.
E to the n.
There's an exponential function here. It's exactly right. Let me just recall for you. This is what's really cool. Not only are we getting a number that's not an integer, we're actually going to have an irrational number showing up in this answer. Do you guys remember that there's a power series for e to the x, right? In your calculus class, it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and this is ... and that converges for all values of x. Well, if I would like to create this expression out of this power series, what number should I put in for x? Not 1. If I put in a 1 for x, everything would be added together. -1, right? -1. So let's just look at that. E to the -1 is 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial. It's exactly what we have there, right? So this limit is equal to e to the -1. It's 1 over e. the probability of a derangement tends towards 1/E. E is about 2.78, something like that. Roughly in the ballpark of 1/3. Okay, you just want to use nice round numbers. It's a little more than that. I think it's actually like 37%, something like that, roughly. But you get this weird oddball number showing up on this hat check problem as you let the number of people at the party go to infinity. I think that's kind of neat. I don't know. You guys think so, but I think it's kind of neat. Any questions here about derangements? My one little caution here is I would suggest you focus on the formula in the box. I do sometimes see people getting this power of -1 did change. So make sure that you're learning, don't confuse yourself between those two formulas. They're of course the same. But if you have them both kind of running around in your head, I could see that being a little bit confusing. Okay, well, that's my little brief discussion of derangements, but then we can generalize that.
So it looks similar to that.
What if the constraint was, what if I didn't say I don't want anybody to get their own hat back? What if we said, I don't want, for myself, I don't want to get Sergio or Ali or Kevin's hat. And then Kevin doesn't want to get Sam's or Marcus's or Alyssa's hat. Like, what if we each had like separate conditions? There would be no reason why you couldn't try to solve that problem as well. It's a little more general than just the derangements problem. So this is actually something called forbidden positions. I want to talk about that now as well. It's the next section, so we're moving right along here. Hopefully I'll get this done, otherwise I have to do it on Thursday. And I think there's a homework problem on this, but if we can't get this done today, we'll just do it on Thursday. So let me set up an example of this, just so you have an idea of how this might work. I might ask you this example. How many permutations of, let's say, I've got 5 numbers here, 1, 2, 3, 4, 5, are there such that, so how many permutations of 5 numbers are there such that, and then I'm going to make some bullet point constraints here. So the first constraint is that 1, 4, and 5 are forbidden from the first position. So you cannot start with a 1 or a 4 or a 5. And then maybe I have another constraint, which is 1 and 3 are forbidden from the second position. Something like that. And I have one more, let's say that 4 is forbidden from the third position. Now, all of that is just one giant big question. So if you label, if you label your positions, we can actually draw a picture of this in a, what I would visualize as a 5 by 5 grid. And I'm going to make 5 rows here. And these 5 rows are going to be the positions. So the first row is position 1. The second row is position 2. In the third row, we have position 3, and so on. Position 4 and position 5. The 5 positions are like that. And I'm now going to draw 5 columns as well. And what I'm saying here is that 1, 4, and 5 are forbidden from the first position. So I cannot put a 1 or a 4 or a 5 in the first position. The only options would be 2 or 3. So we cross off, or we identify the forbidden positions in this picture. On the second position, 1 and 3 are forbidden. And then in the third position, a 4 is forbidden. We can draw it as a little sort of tic-tac-toe board with a lot of squares with X's and spaces. And what we're saying now is, how many ways are there to have all 5 numbers show up in a permutation, but your first number, which is labeled in the first position, has to be a 2 or a 3. The second one has to be a 2 or 4 or 5, and so on. So one example might be to do something like this. I could choose this one, choose this one, choose this one, choose this one, and then choose this one. Right, and now what would that be? Well, in the first position, I have a 2. In the second position, I have a 5. In the third position, I have a 3. In the fourth position, I have a 1. And in the fifth position, I have a 4. This would be a permutation of 1 through 5 that avoids any of the X's, right? And the question would now be, well, how many ways would there be to do this blue dot selection? I've given you one example here, but how many other ways would you have of doing that? And just as a side comment here, the derangements problem is really also can be drawn in this same manner. Let me just show that to you before I go any further with this example. So, I mean, if you're thinking about derangements, it's really a forbidden positions problem. So derangements are a forbidden positions problem. And I can show it to you visually very easily. You just come back and draw this same diagram again. So it's, I guess I'm doing 6 rows here, doesn't really matter, but you have something like that. It's just to get something up here. And all you're doing when you're solving a derangements problem is you're just saying that in the first position, you cannot have a 1. Right? The first person cannot get the first hat back. And in the second position, you cannot have a 2. So every hat goes to somebody other than its owner. So this would be the diagram for the derangements example of the forbidden positions problem. So this is simply a generalization of it, where your conditions are sort of more haphazard. They could be anything. But you can imagine how this would be real world applicable. Dr. Annan cannot teach at 8 a.m., 11 a.m., or noon. Dr. Glesser cannot teach at 8 a.m. or 10 a.m. or whatever, and they want to put one professor in a classroom at each time that fits their schedule, right? So this is kind of a big spreadsheet almost with certain constraints that you cross off. You can see why this would be important, and it'd be nice to know if there's maybe more than one way to do it, or how many ways there are to do it, and try different things. So yeah, that's the idea here. The idea, I guess I should write it down. I still have about 10 minutes. I think I should be okay on this. So the idea here is how many ways can we put one dot in each row and column, avoiding the X positions, which are the forbidden positions. That's really the phraseology we could use for this question. Okay, so now I have to answer the question. We have to answer the question. Maybe I'll come back over here. We're going to do this the same way we did the derangements, which is we're going to take the n factorial, which is the total number of ways of putting one dot in every row and column, disregarding any constraints. We're going to take that n factorial and we're going to subtract the violations. The only issue here is the violations are going to not be quite so cleanly and symmetrically expressible because we got this kind of weird shape of this diagram with the x's kind of all over the place. So we have to be a little bit more general in how we describe this, but it's really not that bad, right? So the way, basically the answer, or the, I guess I'll call it a strategy again, which is what I expressed it as earlier. Right, the strategy here is going to be use subtraction from the n factorial total. So just like with derangements, we took n factorial and we subtracted violations. I'm going to do that here. So what are my violations now? I have to express this slightly differently. Let's let a sub I be the set of permutations with violation in position I. Okay, so A1 would be any permutation where the first number in your permutation was a 1 or a 4 or a 5. That would be A1. A2 would be any permutation where there was a 1 or a 3 in the second position. Right? So I have several types of violations. I can violate row 1, I can violate row 2. Violating row 1 just means I put a blue dot on an X in that row. Violating row 2 would be putting a blue dot on an X in the second row. This is what we don't want, right? This is what we're subtracting from the n factorial. So just like before, the total number of violations is just the size of the union. Okay, and of course you could have more than one violation at a time, which is where this is going to turn into another inclusion exclusion application. Okay, so the violations comprise A1 union A2 union all the way up union dot 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 all the way to A sub n. And so, where is my notation? Right, so the number of valid solutions, or sorry, valid permutations is the number of valid permutations is simply going to be n factorial minus the size of this union. That's what we have to think about. So far, nothing has changed. I mean, this should sound like I'm like a broken record. It's almost the same thing I said for derangements. I've got the same notations, I've got the same strategy. It's all working the same. Where things are going to get interesting is what the sizes of these sets are. So, you know, the next thing to come is, so let's just put equals. I'm just going to keep going here if I could. This is going to be equal to n factorial minus the summation of the sizes of all of the individual a sub i's. And then by the alternating nature of inclusion and exclusion, we would have to add the two-way intersections. And I still need more room here. And I'm not done yet, I just need more room. And then I'll subtract the three-way intersections. And then dot, 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 right? We're just alternating. This is just an alternating expression here. And the last one would be plus -1 to the n times the intersection of all of them. And again, I think I have that right, that if n is odd, we want to subtract this last term, and it's even, we want to add it. So I think my power of -1 is correct on that. But this is what we would have. Now, if we think about the size of A1, again, what is A1? It's a permutation where there's a violation in the first position. But then after we have made sure that we had a violation in the first position, then for the remaining, in this case, 4 rows and 4 blue dots, I can do whatever I want. Right? So yeah, maybe I put my let's use a red dot since it's a violation. I'll put my red dot right there, fine. Then for the remaining 4 rows and the 4 dots I have left, I'm gonna have n-1 factorial ways of filling that out, right? So what it really comes down to is, well, there's an n-1, so let me put this down. What I'm trying to say, maybe not so well, is that every single one of these terms has an n-1 factorial in it. And how many of them are there? So let's think about this example. The number of violations for A1 would have been 3, right? And for each of those 3, I have 4 factorial ways of putting the remaining blue dots in the 4 subsequent rows. But I could do 3 bad things on the first row. Okay, so that would be like for the size of A1. Like if I just to scribble here for a second, the size of A1, I have to make a violation in row 1. There's 3 ways to do that. And then after that, I got 4 factorial ways to go from there. Okay, what about in the second row? If I want to violate the second row, well, I got 2 places I can put my dot that would be a violation in the second row. After I've done that, then the other 4 rows, which are rows 1, 3, 4, and 5, can be permuted however I want. Right? And so on and so on. So you just, the third one has 1, and then the fourth one has 0. There's no ways to make a violation in position 4 or 5. So you'd be adding these up in this summation right here. And how many 4 factorials do we actually end up with? Oh, we had 3 from here, 2 from here, and 1 from here. I am going to call this number R1. Just to be general in the notation. So just give me, I know I'm almost out of time, but let me just kind of finish setting this up. We'll have to practice this on Thursday. But that would be called R1. And in this example, R1 is 6. And just as a little side note, R1 is just the number of X's that you have in total. You might notice that. Oh, there's 1, 2, 3, 4, 5, 6 X's. And if you add these up, you'll get 6 factors of 4 factorial. See that? And then on the next summation, you will have, well, again, 2 of the rows have a violation that you're trying to impose. After you've created a violation in 2 of those rows, the remaining n-2 positions can be filled however you want. And so there will be an n-2 factorial here. And how many of those are there? I'm going to call it R2. Exactly. And then from there, we go on and on and on, minus, plus, dot, 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 dot. The last one, we see that there's a -1 to the n. And now here, the size of the intersection of all of them, that would simply be the number of ways of making a violation in every row, which for this problem would be 0, because you can't make a violation in the 4th or 5th row. But in general, if there are X's in every row, you could manage to hit an X every single row that you have, and there might be R's of n ways to do that. So what this is actually the formula for forbidden positions. And all I need to sort of say is where R sub I is equal to the number of ways to make a violation in I positions. We'll have to practice this on Thursday because I don't have enough time to really get into it now, but R1 is pretty easy. You have to make one violation in one position. It's either here, here, or here. There's 6 different places you can do it. When I'm starting to calculate R2, well, now R2 is actually going to consist of violations of positions 1 and 2, or violations of position 1 and 3, or violations of position 1 and 4, or you have a bunch of them, right? You can take any 2 of them. You can take any 2 of these, there's gonna be 10 terms. And I'm not gonna be expecting people to show their work of how they got these numbers, but I'm gonna ask you to write down 10 numbers added up. You see what I mean? So I got just 1 second to show you like how to calculate this number. This is only if you want to do the homework before Thursday. Because there are a couple of these on the homework. If I wanted to do violations for 1 and 3, that's these 2 rows, right? I have to put my dot on top of an X in row 1 and in row 3. So I could do it, so watch my fingers. I could do it here and here. Or I could do it here and here. I cannot do it here and here because your permutation can't use the same number twice. So your 5 dots are never going in the same row or column as any other dot. So you'd have 1, 2 ways of making that violation, and you would just simply write the number 2 right there. Okay, and you have to do that 10 times. But actually the ones that involve 4s and 5s would all be 0. Because there are no violations in rows 4 and 5 here. So anyway, we'll actually go through this together. I have a group work for us and we'll practice how this theorem really works on Thursday. But this is the formula for it, and that's the whole concept. So it's pretty easy once you get the hang of it. I'm gonna let you go, guys. I have office hours. If anybody wants to stop by and chat, I'll be around now and then also again after 8:30 tonight. See you guys again soon. Thanks for being here.